So I'll get starting the presentation for this afternoon. VPN and IPSec concepts. So this continues on from our WAN concepts chapter. And this one we look at the VPN technology itself, different types of VPNs, and how IPSec is used in this feature. So we can all agree that VPNs carry our information from point A to point B in a secure manner. So this traffic is encrypted to keep our data confidential across whatever network it is going to and from. So in this example here, we are using the public internet as the classic example. So there's various encryption features that are supported under the various VPNs. So we have Internet Protocol Security, IPSec, Secure Socket Layer, SSL, VPNs, just to name two of them. So the major benefits to us that VPNs provide are security, scalability. They are also very cost effective and are very compatible with major vendors of networking equipment. So as long as we have access to a service provider providing internet access, we have the capability to provide a VPN secure connection to our other sites. So basically the way site-to-site VPNs work is we create a VPN on our client gateway, and this gets terminated at our destination, generally on a dedicated VPN gateway. It doesn't have to be a dedicated gateway. It can be another router. Okay, as long as the device has the capability of supporting the connection, we can terminate against it. Now, the reason we tend to use VPN gateways is the added security of firewall protections and a few other nice to have bits, but we can do that in other ways. Next is our remote access VPNs, which are created from our client machine, not from a fixed location. So this is a random IP address that changes all the time. And we use the client application to generate the VPN connection back to our gateway at our destination, such as the office. Okay. So how does this get managed? On this level, we can have server-provided VPNs that are managed and created by the provider of the service. Generally, this would be using MPLS to create, or we can manage them ourselves, which we tend to do with IPSec or GRE or some other technology to provide that. And that way we control which sites are connected via the VPNs. As the enterprise creates and manages these tunnels using either IPSec or SSL. So how does it all work? Well, remote access is typically enabled by the user creating the tunnel. Now, I keep referring to it as a tunnel because that's what these technologies do. They create a secure tunnel for our traffic to travel through. So the client creates the VPN connection. Now, in this example here, we're using an SSL connection to secure our web browsing, and the connection is client-based. So the software is on the client machine, such as Cisco AnyConnect, and this provides secure mobility and must be installed on the end user's device. So some of those solutions, as you saw on the last page, were clientless solutions such as the SSL. Now these come in all different shapes and sizes with different features. So we're not going to cover every single vendor or type. We're just going to cover some of the main points. So IPSec is extensive. It supports all IP-based applications. It has strong two-way authentication and allows for shared keys or digital certificates to be used. It has strong encryption with encryption's keys up to 256 bits. It has a medium level of complexity in that it requires VPN client to be installed on the host, and it has a limited option of connecting to specific devices that are based in its configuration. SSL is limited to only web-based applications and file sharing. It also has moderate authentication strength, as it can be one-way or two-way. It's got weaker key lengths, so it's classed as moderate to strong because it starts as low as 40 bits in its key strength and goes up to 256. So that's where it's moderate to strong. It has very low complexity because all what you need is a web browser, and it has extensive options. Basically, if you've got a web browser, you can use SSL. So as we've said, site-to-site VPNs connect two networks across untrusted infrastructure. So basically we send unencrypted traffic through the tunnel. Okay, the gateway does the encryption and decryption. So we have what's called clear text messages leaving our end device, going to the VPN gateway that we're using, has the tunnel to our destination, and it's responsible for encrypting all of that outbound traffic and decrypting any traffic coming back. The VPN gateway at the other end is responsible for stripping and decrypting all the additional VPN headers and forwarding the packet towards the host destination inside our private network again. Excuse me. The traffic that we send only sees the endpoints of the tunnel. It is not aware of any devices it travels via between those two endpoints because it's embedded in the encrypted packet. Generic routing encapsulation is non-secure site-to-site VPN tunneling. It can encapsulate various network protocols and even allow multicast and broadcast traffic to travel across the tunnel. By default, it doesn't support encryption, so that's why it's classed as an unsecure VPN tunnel. It still is a virtual private network in that it provides encapsulation, but it is not an encrypted service. So standard IPSec VPNs can only create secure tunnels for unicast traffic. It doesn't support broadcast and multicast. But encapsulating GRA into the IPSec tunnel allows multicast routing updates to be sent through. So we're putting a tunnel inside a tunnel. We're double wrapping. Now, because of this, it gets a little messy. So we need to be very careful how we look at things. So the passenger protocol is the original packet that's encapsulated by the GRE, whether it be IPv4 or v6 or whatever the message is. The GRE carrier protocol, which has encapsulated the original message, is now transported inside the IPSec. If you're double wrapping. So they refer to this as the transport protocol, this outer wrap. That's the one that the IP addressing stipulates the destination on. So in this example, we are connecting between a branch and a HQ unit and exchanging OSPF routing information via the IPSec tunnel. So as we said, IPSec tunnel only allows unicast traffic. So we need to create this secondary tunnel to allow this OSPF to be transported. So this is where it breaks it down for us. So the OSPF packet is the passenger protocol, and that's encapsulated by the GRE's carrier protocol, which is in turn encapsulated in the IPSec transport tunnel protocol. So if we go back the slide, there's the passenger protocol, that's our OSPF. It's encapsulated in GRE, being the carrier protocol, and then the IPSec being the transport protocol. That's what this slide is showing us. So as you can see, we have a tunnel, and our traffic. So that OSPF packet is protected by two VPNs between the branch and HQ. Now, this site-to-site system comes a little unstuck as companies expand and we need to get to multiple destinations. So they created dynamic multi-point VPNs. This is driven by Cisco software, building multiple VPNs that can be managed easily, dynamically, and scales as we need to. So this uses the hub and spoke topology that we talked about in the last chapter, and it allows spoke sites to establish secure VPN tunnels back to the hub, and each site can exchange its routing protocols and other items like that to allow dynamic support using GRE. Now, it's a little additional version. It's the multi-point GRE, but it's the same principle. Well, what we're doing is putting a tunnel inside another tunnel that allows us to do multiple spoke-to-spoke tunnels within a hub and spoke environment. So basically, an IPSec virtual tunnel interface is set up to allow this to occur. So these configurations are applied to the virtual interface instead of mapping it to a physical interface. And this virtual interface is capable of sending and receiving both IP unicast and multicast encrypted traffic. And this allows for more flexibility and provides different solutions on the fly. So the next VPN we're going to look at is multi-protocol label switching, MPLS. Now, this is classed as a secure server-provided service because the clients of the service provider will not and cannot see your traffic. Okay, so it's a fully managed VPN solution and provides you site-to-site access as you have specified. You can either have a layer 3 or layer 2 MPLS VPN. Layer 3 allows for routing to be established and peering between the various client routers through the service provider's network. The layer 2, the customer routing is not involved. Instead, the provider deploys virtual private LAN service to emulate an Ethernet multi-access LAN segment over which the MPLS network sort of runs. So there's no routing. Customer routers effectively belong to the same multi-access network. So as far as they're concerned, it's like having a big switch in between them all. Oh look, there's a video at this point in time as you go through the online curriculum. So IPSec is an industry standard which defines how VPNs can secure IP networks. It provides confidentiality via the encryption. It provides integrity by hashing, so it ensures that nothing has been modified in transit. It provides origin authentication via the IPSec protocol, and Diffie-Hellman is used to secure the key exchange once this is done. So the way this works is you have a set of pre-shared keys that forms the IPSec tunnel, and then Diffie-Hellman generates dynamic keys and does a key exchange inside the IPSec tunnel. So again, we're using multiple tunnels to provide security. So we have combinations that can be used. So we don't have a fixed, you must use this. The way it was set up was that it could integrate new technologies as they're developed. So it's modular in its design. So all what they've got to do when they develop new algorithms and things like that is write a new module for IPSec so that the new algorithm is supported. Okay, so as you can see from the graphic, we can see what items coincide to whichever point in the module. So effectively, when we're talking about the IPSec protocol, we get to choose which one of these we're going to use. So these are the modules, and we drop them in place, and the combination of the modules that we choose, we get to create our individual specific IPSec tunnel using individual choices. So yes, there's a limited combination of choices that we can make, but it gives us greater flexibility through choice. So each time we create our endpoints, it gives us a unique security association between those endpoints. So first, we need to work out the encapsulation that we're going to use with the IPSec headers. So we can use the straight authentication header or encapsulation security protocol, ASP, or we can combine those two and mash them up together. So AH, you only want to use if you don't need confidentiality. ASP provides both confidentiality and authentication. And that graphics are out of whack. So what's confidentiality? This is dependent on the encryption, but basically we're hiding the message. So we're encrypting it so that the message cannot be read while in transit. The shorter the key, the easier it is to break the encryption. So we have a combination of standard encryptions, and these use different key strengths. So we start off with 56 keys with the DES, then we've got triple DES, and basically what triple DES does is it runs it through the encryption 3 times. So you go through DES, The output is then put back in as input, run through a second time. Then that output is taken back and run through for a third time, and then that is sent. That's what triple DES is. AES has variable key length, so 128, 192, and 256 bits. So this allows for much stronger encryption than the other options. And then we have SEAL, which is a stream cipher, which continually encrypts blocks of data using a 160-bit key. Integrity options. This is the hashing algorithm that we use to confirm the payload hasn't been modified. So we can use SHA or MD5. Okay, so MD5 is a 128-bit shared secret key. SHA uses a 160-bit secret key. And they're the two key lengths options that we use in the hash system. Next, we have authentication. We have the good old pre-shared key, which we need to enter in both ends where we're forming the tunnel manually. This is easy to configure, doesn't scale well, and very easy to make a mistake and not have your tunnels come up. Just saying. Yes, been there, done that. It's rather interesting to troubleshoot, especially if you don't have remote access to both ends at the same time. All right, RSA was Rivas, Shimar, and Adelman algorithm, which allows us to authenticate with a peer before the tunnel is considered secure. Now, Diffie-Hellman allows two peers to establish a set of keys dynamically. And what we do is we select the group, and the group determines how many bits we're going to use in the key. And this changes. As you can see, groups 1, 2, and 5 are no longer used. And I can remember setting up Diffie-Hellman groups with 5. So it's not that long since they've been dropped. Or am I just showing my age? I could be just showing my age. Okay, so please pay attention to the videos during the online curriculum. They will help you get a visual understanding of what's going on. And do any activities that pop up along the course. VPNs are a tricky little beast and can be interesting to actually form and troubleshoot. So, in summary, we had an overview of how VPNs are used, their benefits, their different forms, so site-to-site, hub and spoke, remote access. So we had a look at using dedicated hardware to form the tunnels and client software applications that can form tunnels, and different versions of software can provide different features within forming the VPNs. We looked at how we can use tunnels inside of tunnels, such as GRE being used so that it provides multicast and broadcast features across IPSec, which doesn't support those traffic types. We looked at Cisco's solution for doing dynamic multiple VPN tunnels, and we looked at virtual tunnel interfaces as well to provide simple configuration process when supporting multiple sites, as we can configure the tunnels on the virtual interface rather than on a physical interface. So we can support multiple. We then looked at how IPSec provides confidentiality, integrity, authentication, and can exchange keys dynamically. We looked at the different algorithms and key links to give us a unique combination that allows us to have a unique IPSec tunnel with the features that we wish to have. So not only do hackers need to break through multiple tunnels, they've got to crack an unknown combination of features before getting access to our information. All of this combined means our data is safer for longer. And that brings us to the end of the Module 8 presentation. Any questions from anyone? No, the usual silence. Okay. As usual, I'm available via WeChat or email, and I'll answer your questions as you get to them as you go through the module. I'll check back in around the 4 o'clock mark, your time, and see how you're progressing. Now, Chapter 8 allows me to trigger the next module exam. I think I'll turn that on tomorrow, as most of you have stuff to go on with. So this gives you a chance to read and refresh 6, 7, and 8, and I'll turn that series of exams on tomorrow morning. All right, bye from me for now. I'll check back in at 4 o'clock.